Well, hello everybody. Welcome to this little training session on materials, which is the continuation of what we did the last time on the basics of or the fundamentals of hydraulic sealing. So you had the chance to listen possibly to our last session, which gave you an idea of sealing fundamentals on shapes, on criteria, on a little bit of materials. We didn't touch too much on that. So this presentation here, we'll be talking strictly on materials and some of the parameters that you need to look at and some of the terminology that's used in the industry, hoping that make your life a little bit easier. So, welcome, as it says, welcome to the show. Choosing the right material is the key to your success. You can have the right shape, you can study everything about pressures and temperatures, but if the material doesn't really fit the application to a T, you're not going to get long life, you're not going to get long service. Of course, if you have nothing else in the pantry, you can choose whatever you got at hand, but when you have a chance to look at your parameters and make an educated guess on what's going to work best, the right material, key to your success, longevity, performance, etc. So we'll take a look at different things today. And this is a little bit of a repeat from the past presentation on basic sealing fundamentals. And people think I'm very repetitive on those things, but it's key. It's key, and I insist on the selection made according to the following criteria, which it's much more than touch base. We talked extensively about that on the last presentation. So, following criteria: temperature limits of your specific application, and I will maybe put a bit of emphasis on the limits, so you really have to take a look at the extremes and the cycling that you'll see on both ends. And geographically, depending where you live or where the equipment that you're servicing is located, the limits become important. Example, we're filming this from Montreal. Well, if you live in British Columbia or if you live in southern US, the limits are going to move, so you have to take that into consideration. The range of pressure ratings that the seal will be encountering, so we talked about that also last time, but from low pressure, which is at 0, or even perhaps a vacuum application, up to the upper limits of your system's pressure, and including the pressure spikes that the system might be seeing if you're working especially in construction equipment, where you can get a lot of shock loading if you're in mining or forestry. So you have to look at that. Chemical products and contaminants that will be in contact with the sealing material. That means not only what's theoretically in the unit as far as fluid that is being pumped through, but also the other chemical products, greases, lubricants, outside contaminants that might be drawn into the system. You have to look at that too. Your anticipated usage, and here's something interesting. We can sell some very exotic and expensive material that's bulletproof, and they'll give you more service than you could shake a stick at. However, that's maybe not what you need, and maybe that's not where you want to spend your money. So you really have to look at your anticipated usage. What are you going to be doing? You don't want to overkill, you don't want to overspend, but then again, you want to have the minimum requirements. So it's really you, the customer, is the person who's going to decide what your usage is. And the other thing, desired seal life. Some people will repair units that are at the end of their lifespan, and they'll just need to put something in there to last for the next month or year or whatever. And some people, and I'll just take an example, and I use it all the time because I'm not smart enough to find other applications, but we do a lot of business in hydroelectricity. When you get into a hydroelectric turbine, oftentimes the seal life has to be 40 years. And so when it's 40 years, you choose a material, not only a configuration, but a material that will give you 40 years lifespan. So you have to take that in consideration. Good. So we keep those criteria in the back of our minds, in our toolbox. Important to respect those. Moving right along. We're looking at this graph here, and it says pressure limits for Parker packing compounds. And we'll go back to what we said last time. It just happens to be a slide that's taken out of a Parker catalog. This is not made to specifically promote only Parker products. We thought it was a pretty useful graph for you to look at. And it's talking about pressure ratings, which is kind of neat. I kind of like that one because it gives you the wide spectrum of different materials that you can find in a cylinder or in associated equipment. And we're going from, well, you can see from the graph up and down who's hard, who's soft, who can hold, who can. So we're looking in the lower pressure ratings, you've got all your rubbers, 70 Shore, 80 Shore, 90 Shore. Then you go into your polyurethanes. Then we get into the plastics on the Shore D scale. We'll talk about that in a little while. So the plastics, your nylon, and then at the end you've got your filled PTFEs, which for you and me call it Teflon, but we can't call it Teflon. It was just, you know, like you ride a snowmobile, not a skidoo, but we call them skidoos here out in the east, cuz. Well, PTFEs or Teflons for all intents and purposes. So it gives you a range. So as the material gets harder, your pressure limits become higher. But as we said in the last presentation, what makes a seal work is resilience, conformity, able to to follow the peaks and valleys of surface finish. So all these materials that will take you to high pressures will not necessarily seal very well because they're very hard, so they don't conform. So we'll go back to what we said. It's always, you know, it's always a question of compromise. So depending what you're looking for, and that's why you go back to that slide before, depends on your expectations of your application. So anyways, this is just to give you a rough idea of what we have available in the standard ranges of materials, a little bit of a description. And we'll be looking at the soft and the hard materials. We'll be looking at what's in the family of rubbers, what's in the family of plastics. And in the plastics, we can go anywhere from nylons to PTFEs, etc. And in the rubber products, you know, your typical nitrils and fluorocarbons and EPDMs. And we'll be talking a little bit about cross-linking, and we'll actually, I'm going to jump forward. I'm going to do something that in a presentation like this is perfectly uncouth. And I'm going to move forward, and then we'll backtrack to come back to those nice little graphs. And well, nobody said the presentation was going to be perfect, but you'll have to bear with me on this one. So we have various families, and we're just trying to give you some of the general names of families that you'll find that we'll typically see in our sealing industry. So we're going to talk about thermoset polymers. We'll take a look at that. We'll look at thermoplastics, and we'll work on the difference between those two. Fibers, which are often used for reinforcements. PTFE, the whole family of Teflons, to pardon the trade name usage, but so the PTFEs, you know, filled or unfilled, and a little bit on metals, which are, you know, 2 or 3% or something, but they work and they're used, so we'll discuss. Elastomers are part of the thermoset polymer family, and I like the term thermoset, which means that once they're produced, they're set, that's done. It's whatever transformation takes place, is finito. Okay? So they are polymers that have been cross-linked, could give them flexibility. And if we're to move back, like I said, things that I shouldn't have done, but you'll have. What happens when you cross-link a polymer? What you're actually doing is your thermoplastic, because we're comparing two. We're looking at thermosets, and you look at the thermosets, you got all these cross-linking points where one strand can move into the next. When the thermoplastic polymer chain, you can have branches, but they never touch, they never cross. Okay? This side gives you flexibility, this side does not. And just to give you an idea, I compare these two to a road map. And let's say you're on these highways here that never cross. Well, if you miss an exit on the highway and you're on the thermoplastic highway, well, trying to get back in the other lane is nigh to impossible. They never cross. So your whole commuting is very rigid, is very unflexible, because if you miss your exit, you can never come back, or maybe 50 miles later. Your rubber highway, your thermoset highway, is full of crosslinks. So you got all these overpasses, you got these exits and overpasses, so you miss one, you can use this one, and then you can use that one. Your whole commuting becomes flexible, and we're doing that with materials. Our material highway is one of flexibility. And if we go back to the chart that says, oh yes, the plastics takes high pressure. Yeah, they're high pressure, but they're not flexible, so they're not going to seal well. So we're going to spend some time on thermoset, and the English language has it for once better than the French language. In French language, the thermoset, they call it thermosetable, but they're not able, because when we buy them, they're thermoset, period. The process is complete, so we are going back. Okay, so they are polymers that have been cross-linked to give them flexibility. It's all that cross-linking, those overpassing of your highway, those exits and those crossovers. It permits you to get something like this. You know, it's flexible, it turns. So when you compress this in a groove, it's gonna follow the whatever compression you give it. So it becomes, the flexibility gives you conformity, the conformity gives you sealability. So that's why we like using thermosets for actual sealing material, because of that flexibility. But they cannot be transformed once cured. So once cured, your goose is cooked. Ono will melt them again, or will weld them, or will reprocess them. No, sorry, done, said and done, nothing. Nothing to be done, it's complete. So that's why they use the term set. It's set. You know, we say set in stone. These ones are set in rubber and you can't change. Their hardness is measured on the short A scale, generally in the range of 40 to 90 hardness readings. And all you purists out there, or those who hold a very pedantic knowledge of the Shore scale, you say, no, but it can go on. In our business, 40 to 90, 40 being the softest, 90 the hardest. If you look at Shore A, the Shore A scale is a scale that was developed by an American metallurgist called Albert Ferdinand Shore, and I sound very historically perfect, but 5 minutes ago I had to check Google to remember what his first name was. It was Albert. Anyways, he devised a scale that will, for us, it separates rubbers, elastomers, and plastics. Your Shore A typically for rubber compounds, your Shore D for anything that's PTFEs, nylons, what else would we use in this industry in the plastics? PVCs, ABS, polypropylenes, okay? So that's kind of what you get in the thermoset. Okay? And when we say thermoset, we say elastomer are part of the rubber polymer, but we call them thermosets because it sounds complicated and it sounds classy. And you can name drop that on Friday nights when you have a beer with your buddies. Tell me you know thermosets. It's, ooh, what's a thermoset? Just a rubber. Examples, your standard elastomers that you'll find in most catalogs, that you'll find in most static and dynamic sealing applications, base rubbers, the nitrils, the fluorocarbons, again, like Teflon that we call PTFEs, fluorocarbon, most people call them Vitons because that's a DuPont trade name, but their generic term is fluorocarbon. Ethylene, propylene, which oftentimes in the industry is called under its abbreviation. They call it the EP, and the DM is, I could talk for hours about what the DM means, but anyways, EP, EPDM, silicones, and polyurethanes. There's some of our more popular things. And remember, we're doing this presentation not for sealing all general applications. We're really looking at sealing applications with materials in the industry of hydraulic and pneumatic cylinder rebuild or manufacturing. So that's kind of your standard ones. Thermoplastics, they're the ones that don't have any overpasses on the highway, okay? So thermoplastics, or we could call them plastics in general, very hard, very rigid, but they're polymers that become soft or moldable at higher temperatures and that subsequently harden as they cool off. They inherently have, which means you can bend and meld and remold and bond, and a lot of hot bonding and this and that. You can do that because of they don't have any cross links and they're not thermoset. High molecular weight, not that that makes a big difference for you. I mean, I've never really checked my different plastics what the molecular weight is, but that's typical characteristic. They can be bent, they can be welded, hot bonded, reshaped once molded. So you can do different stuff with it. And their hardness is measured on the short D scale. So you have to be careful when people talk about the Shore scale. It's which one? The A's are for rubbers, the D's are for plastics as a general guideline. And generally in the range of 10 to 80 hardness readings. And important, the Shore A scale and the Shore D scale, on the numbers, they're offset. So it's difficult to compare a Shore A to a Shore D because the scales are offset, so you can't say, well, it's like a rubber, but it's a lot harder because the rubber is a 50 and your plastic is a 60, they're probably way offset. So you really have to look at them independently. What else we got? Examples. Nylon, UHMW, polyethylene, polypropylene, ABS, and I could go on. What else we got? We got Delorins, and we got, anyways, that whole family, PVC, that kind of stuff. Okay? Now, here's where it's important. The difference between the thermoset that has flexibility, thermoplastics have no resilience, okay? Nor any conformity against their mating surfaces. That means that once they're installed in a groove, they're not going to move along with the pressure. I can bend this piece of rubber, but I can't bend this piece of glass filled nylon, okay? This is a thermoplastic, this is a thermoset. So it makes all the difference in the world. When thermoplastics are used as sealing element, because if you look at this two-piece piston ring set, this is the sealing element in the sense that rides up against the mating surface, and you say, yeah, but you just said that this thing doesn't have any conformity, so it's not going to seal. Well, when used as a sealing element, they usually require a preloading mechanism commonly using no, there's a D2, that's my mistake, an elastomeric element. So here we look at this two-piece seal, and we are preloading this piece that doesn't move with a piece of rubber underneath in the groove that it moves. So it's gonna, as it moves, it's gonna create pressure on that outside sealing ring. That's a thermoplastic to actually activate it. Of course, the thermoplastics being harder, they're not going to conform to the surfaces as much, but you're hoping that this rubber ring underneath here is going to create enough pressure to create a sealing line here, even though it's a thermoplastic and not a thermoset. Does that work for you? I hope it does. More than often, thermoplastics are used as auxiliaries to the sealing function. So auxiliaries is another fancy word that we use in our industry to say anything that will help the seal do its job, but that typically doesn't actually do the sealing work. Example, a backup ring. Backup rings are there to protect your seal that's in front, like an O-ring in a backup, from extruding. Guiding elements, like these babies here, you know, they're there to guide, to make sure you don't have any eccentricity, and anti-extrusion devices. So that's what thermoplastics are used for. I often use cooking. For those who are good cooks, I often use references to culinary references to thermosets and thermoplastics, and I'm sure a lot of you wake up early in the morning and go to work, and if you're like me, sometimes I wake up a little late, so you're in a rush. And when I drive out of the house and I check our fast food friends out there with big lineups, yeah, people like to go pick up their breakfast at the pickup counter at your local purveyor, whether it was named after an ex-hockey player or if it's a Golden Arches or whatever. And a lot of people enjoy having, you know, a sandwich that has egg and cheese in it. So here's the analogy for today. For I am the Julia Child. That probably doesn't ring a bell to everybody. That's about 50 years ago. Who else cooks? Gordon Ramsay? Anyways, I won't get into that. Your egg and cheese sandwich. Well, let's watch how that works. So you cook an egg. Your egg is cooked, right? Once it's cooked, it's set. So your rubber is kind of a cooked egg. You like it scrambled? Okay, here it is, it's scrambled. But you can't turn around and say, nah, can you change that and make it a fried egg? No, sorry, too late, thermoset, your egg is thermoset. But in your sandwich is a slice of cheese. The cheese. Well, you can melt the cheese, but if you melted it and you want to freeze it and then grind it and shred it to put in your tacos or remold it into something else. So your cheese is a thermoplastic, and that wouldn't surprise me that a lot of the cheese that we buy, generic cheese in the grocery store, actually has plastic in it, but I digress. Whereas your egg is thermoset. I don't know if that helps, but so much for Julia Child. We're moving along. I hope that helps as an analogy. Okay, we've got textiles too. Now there's a certain amount of textile that we use in the industry, and they're fiber-based substances that can be spun or woven. So basically, textiles, there's about 2 ways to make your textiles. If you go to your local museum of how things used to be done in the past, you know, you used to spin your yarn on a spinning wheel, or you used to make your blankets on a loom. The industry hasn't changed all that much, except the machines are probably more modern, but that's no difference. What do we use textiles for? Okay, those fiber-based substances, they're usually used for reinforcing elements for thermoset elastomers or thermoplastics example, we'll show you a set of a product that is still used. It's a dying breed, but you'll still see a lot in repairs. Well, we can't call them Chevron because that's a trade name too. V-packings, stackable V-packings, a lot of those V-rings, and it's going to be hard to see on camera, but these are reinforced. This would be your equivalent rubber piece or elastomeric, so I can bend it like this. And then in the middle, to make it a little harder, I can't bend this one because it's got fabric reinforcement inside the rubber. Okay, so these fiber base we use as a reinforcing element, okay, within. So oftentimes these sets are staggered, so you'll get the softness and the resilience of the thermoset elastomer, and you'll get the hardness, the pressure rating of the fiber that's going to reinforce. Or sometimes you also use the adapters on each side with our thermoplastics, because we saw the thermoplastics, the nylons will take you up way higher pressures. So what you're doing, you're making a, well, if only I could put them in the right order, look a little bit more professional. There you go. So if you look at the first three products we've looked at in example, a set of V-packing, so your adapters, male and female, which are really the ones seeing the pressure, well, they're out of the thermoplastic because they're really hard and they don't seal. They're there to support the stack. So we don't really care if, because they're a thermoplastic, they don't have the resilience. Okay? When we need low pressure sealability or good conformity, then we use these elastomeric rings, these thermosets. We've got two in this set. But what did we say about thermosets? Well, they're measured on the A scale, so they're soft. So if you have high pressure, maybe a little too soft. So in between, we add these elastomeric base, but textile reinforcing elements for thermoset elastomers or thermoplastics. The fiber in thermoplastics is usually more into things like wear bands, guiding rings, and in the thermosets, fabric textiles with thermosets are made to help out during extrusions. So this is just an example. Okay. Example, cotton. Example, these, what we just saw, these fabric reinforced, it's cotton. Didn't write it down here, and we did this presentation in French before, and I didn't mention it there because language is language. Cotton in that industry, especially in the hydraulics, if you see the word duck, it's not a mallard that got stuck in your computers, in your hydraulic system. I don't know where that comes from, but duck is another word for the cotton that you use in reinforcement. And a little analogy that it took me years to catch on. I'm sure everybody's toolbox has at least one roll of duct tape. Now, a lot of people call duct tape, and they write it D-U-C-T, because they think it's used to wrap around ducts to hold parts together. But actually, you'll see some brands that write it duct tape, D-U-C-K, and people say, why do they call it duct tape? Well, because in the industry back in the days, duct, for whatever reason, was the cotton, and your duct tape is actually a tape that has reinforcing fibers, usually cotton, so it's called duct tape, D-U-C-K. When you see duck, you're not at the zoo, you're in hydraulic seals, and it's another word for cotton. I don't know, was that of any use? It's a duck à l'orange, that's a orange duct tape, whatever. Okay, fiberglass cloth or polyester cloth, used oftentimes, especially in guiding elements, wear bands, things of the sort. So again, textile based, we never seal extensively with textile, except there's one exception. I think we'll see that later. I should know, I wrote this stuff. But other than that, mostly for reinforcement, but they're part of the ceiling story, so you'll know that they're available. Cotton fiber is often used to reinforce homogeneous rubber, i.e. V-packings. We saw that a few minutes ago in piston cups. Fiberglass and polyester cloth is often used in conjunction with phenolic, polyester, or epoxy resins. Since we're in that little second bullet point here, one thing that might start getting you scared, phenolic, which is phenol resin, was used many, many years as your base resin, and they put it with fiber and they make guiding rings. People are starting getting scared of the term phenolic because theoretically phenol resin could be a known carcinogen, and people don't like machining that stuff. And that's why most of the bearing rings that are fabric reinforced will use polyester fabric, but they'll also use polyester or epoxy resin, and everybody feels comfy when you use those. Okay, fiber-based materials are also used in the fabrication of mechanical packings, most often with a lubrication agent added to the braid. It's this baby here, this braided packing. We're not going to discuss that, but at least you know it exists. That will be part in our future training sessions of a whole section on mechanical packing that you usually find into process industry pumps and valves, etc. Expansion joints once in a while. But this is one of the rare applications where you're using fabric as the actual dynamic seal. But it, you know, if you have this in your cylinder heads, your equipment is probably at least 50 or 60 years old, so the risk of you seeing it on your repair bench or night are very unlikely. The PTFE family. PTFE is a thermoplastic. So if it is a thermoplastic, why didn't I talk about it before with the other ones? From the family of the ethylene-based polymers, that's just to make the slide look nice. Because until I looked it up, I wasn't too sure. Yeah, in the ethylene, and there's a lot of fluorine content, and there's no fluorine carbon bonding in PTFEs, but that's all chemical. We don't really care about that today. But usually known by its commercial trade name of Teflon. Why we separate the PTFE? It's got, as a thermoplastic, it's got some really neat characteristics, which, going back to Julia Child and cooking your thermoset egg in the skillet, okay? And usually your thermoset egg in the skillet, oftentimes it is lined with some ethylene-based polymer in the bottom of your skillet. And they said, oh, using the Teflon lined skillet, yes. And why do you use a Teflon lined skillet? It's because it has an extremely low coefficient of friction. So when you're cooking your egg in the morning, you don't have to put half a pound of butter so it doesn't stick, right? You just hit it right in there and it doesn't, and just flip it easily, and then you get your thermoset egg. Okay, but, so it has unique characteristics such as PTFEs are chemically inert. Why do we mean by chemically inert? You can take a piece of PTFE like this, and then you can have all your ingredients on the table. You could have a jar full of acetone, and then you could have a jar of sulfuric acid, and then you could have a jar of paint thinner, and then you can have a jar of hydraulic oil, and you can, do a dunk test, and then the dunk test, and then the dunk test. And if you take this rubber, well, I'm saying dunk test over time, you'll put this one in acetone and it'll swell in half an hour fast, and you put petroleum or you put silicone parts in something else. Anyways, you always have to check your compatibility rating for all your elastomers to make sure that they'll hold up. Remember on that, I don't want to go back to that second slide, but we said make sure that you know, the fluids or the contaminants that are going to be in contact with your seal are compatible. Nice thing with PTFE, it's chemically inert. So anything that touches PTFE, I mean, there's a couple of really weird, except like liquid alkali, molten alkali metals like sodium, and you know, some of those that have to be kept in oil. Or here's another of my favorite, I think uranium hexafluoride or something really weird that we've never seen. So forget the really weird exceptions. Usually PTFE is chemically inert. So once you're using PTFE, go to bed at night, sleep well, you know, nothing's going to happen. Your PTFE is chemically inert. It's got a really wide temperature range. Okay. It'll take you up to about 275 degrees C, and it'll take you down to the cryogenics, so the liquid, your liquid gases, without without being detrimental to the product. And we go back to extremely low coefficient of friction. You know, even all your lock de-icers that are, say, that have a PTFE based, okay, so that it de-ices your lock and it leaves a little coat of low coefficient of friction. So I was going to say, so you can slide your key in the lock, but nobody slides keys in locks anymore, right? Everybody's remotes, except for my 61 Plymouth. It's still like that, but we don't worry about it because it's warehoused for the winter. But you know, but it has low coefficient of friction. So that's what we like about PTFE. It's got some great advantage, but what is it? It's thermoplastic. So what's a thermoplastic? Okay, so I can bend this in two, and guess what? It stays bent in two. Okay, well, I can mechanically bring it back, but if you have this in a system where you expect it to take back its original shape, because that's what creates the sealing line, is the constant pressure of the seal when it's being flipped around, wants to come back immediately to its original shape. It doesn't seal very well, but it does other things well. So oftentimes it's called mix and match. The disadvantage of using PTFE, I showed you on the last one, you know, low coefficient of friction, wide temperature range, it's chemically inert, blah, 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 blah. Great, but PTFE in its virgin state, usually virgin PTFE, usually it's white, okay? And it has poor mechanical properties. What are poor mechanical properties? Well, it creeps. If you compress virgin PTFE, it'll just try to escape the pressure. So I could put this between two platens and put some pressure on it, and instead of, it will be kind of rolling your dough, going back to Julia Child, doing some pastry work, you know, as the roller comes down on your pastry. Any of you cook any pies out there? I don't know. Anyways, there you go. Everybody eats pizza, it's all right. So you toss the pizza dough up in the air and it stretches. Well, kind of virgin PTFE, like you toss your rings up in the air and they stretch. Not, anyways, that kind of stuff. Has poor mechanical properties. Okay, and the other thing, it wears fast. Even though it has a low coefficient of friction, if you get any abrasives against virgin PTFE, it doesn't really hold up against the wear and tear. Okay, so to offset the poor mechanical properties, PTFE is often filled. Use a filler agent to offset this drawback. Commonly used filler agent. So what you do when you're molding or compressing your PTFE resin, you add fillers. Fiberglass, carbon fiber, bronze powder, graphite. I didn't even check micro glass beads. All these things that will give you better mechanical properties, better wear resistance, and it will also avoid the parts from under pressure from creeping. Those fillers will keep it together when you add pressure. Okay? So oftentimes we'll say, oh, give me a bronze-filled PTFE ring, give me a glass-filled PTFE ring, I want a graphite-filled wear band, or things like that. That's why we use those fillers. It's because PTFE, if you're using a wear band or a backup ring or things like that in virgin PTFE, it'll probably lose its shape quicker than if you use something that's filled. And the only reason why you might want to use PTFE in its virgin state is if you're using it in sanitary application, then probably you can't use these. It has to stay something that you, because PTFE, I don't suggest you eat that as snacks at night, but if you were to swallow a piece of PTFE, actually there's a lot of medical reconstruction, like suture thread or joints or that are used in the system that are made of virgin PTFE, because PTFE, we said it's chemically inert and it doesn't react, so it doesn't get rejected by the body. So oftentimes if you're using it in sanitary applications, they don't like having fillers there, okay? Because some of them could be, perish the thought, known carcinogens. Disadvantage of using PTFE: regularly used as dynamic seals on rod and piston seals. Since they're part of the thermoplastic group of polymers, they require a preload auxiliary device, usually made from an elastomeric material, to function properly as a sealing device. Okay, it's just what we showed you with this other one here. You'll have a ring of PTFE and there'll be a loader ring underneath. Whether it's for a piston, whether for its rod, you know, on the static side you'll be using an elastomeric ring to help preload. So remember the whole compromise story, and that's where this becomes interesting. When you start to look at, everybody talks about hybrids now. Of course we talk about hybrids because that's the car industry. A lot of our seals are hybrids too. So you bring in a PTFE, which is a thermoplastic, does a seal well, does it with resilience, but you like its physical characteristics, as friction, it says good temperature range, it's chemically inert. But used by itself, it doesn't work. And if you put just a rubber seal underneath, well, it wears fast, it's soft, it doesn't have a good pressure. But when you use them together, then you get a good wedding, you get a good marriage, good compromise. So it's important to know your limits of PTFE, but PTFE is a great material. I mean, it's used extensively day to day. It just has to be used with something else in the hydraulic sealing industry to make it work properly. So I hope that helps. Metals. Do we have metals? Yes. Used very infrequently as a seal, unless I'm wrong. The cast iron piston rings are used on the high pressure hydraulic applications and areas where extrusion is a problem. You'll see them on double acting cylinders that have to pass over a port. As you see here, this is hard, huh? A black piece. No, there's that. All right, let's make this work. At least you know it's hard, if the picture won't tell you. Okay, so it's very, very hard. And so, well, how can it seal when you've just told us that it has to be resilient and it has to be able to adapt to the surfaces on which it's going to ride? What you're doing with these, you're sealing to a certain extent. You notice also they have to be split. Like all these hard materials, the hard thermoplastics have to be split, or else you could never slide them over the piston, or like this baby here, they're all split. PTFEs, to a certain point, though they're a thermoplastic, PTFE can be stretched to a certain limit, but then usually you have to take a ring compressor to resize them to the proper diameter. But when you're using cast iron and you're going over places where the seal, if it were in any softer material, would destroy itself, usually nylons and especially cast irons, they're bulletproof. The other place, remember, That was my second slide. When we said, you know, you have to tell them what kind of service life you expect. Well, in service life, if you're using cast iron rings and everything being equal, they never wear out. They're basically, you put one in and then you'll probably be, let's be polite, you'll probably be retired or maybe dead before they have to be changed again. I mean, unless something drastic happens. You know, we have applications, and again, I go back to my hydro turbine application, but once you've put together a servo motor using these things, and the servo motor is stuck in the on the top shelf of the turbine well, and there's a 150-ton alternator sitting on top. Don't want to take those things apart ever if you don't have to. So usually they use cast irons. But what happens about sealability? Well, then you know you can calculate your leakage rates with these, and you can compensate with maybe more a higher output, higher flow output on your pump to compensate for the bypass that these babies will give you. So all I'm saying, cast iron exists. We also see it sometimes in wear bands, cast iron wear bands. Very important, and not that I have to teach you anything new, must be made of a material that will be softer than the adjacent dynamic surfaces so that you don't score. So that's why a lot of cast iron is softer than your steel tubing, so you should be okay, unless of course something breaks, and that's the only danger with cast iron rings. If they're improperly installed and they're stretched over the limit and something breaks, then you get cast iron shrapnel inside your cylinder and score all the walls. Major disaster, but whatever. Common metals used in the sealing industry: bronze, brass. I don't know why we wrote bronze. Bronze is more used for making statues than anything else. And bronze is has a tin filler instead of a zinc filler, so it's more expensive. Mostly in the industry is brass, and I think your most common brass alloy that's used in the industry is SAE 660, but brass, and a lot of people, like this guiding ring here, is made out of SAE 660 brass, so it's nice. It's hard. It's got all the strength application, but it's going to be softer than your mating surfaces, so it's not going to score. At least shouldn't. Cast iron, ductile iron. Cast iron is less of an interest now, because cast iron is more brittle than ductile, and people, when they use these piston rings, the big scare of that, as I said before, is if one breaks. And ductile iron is a little bit more flexible than cast. Cast is more brittle. Ductile was basically, I wouldn't say invented, but it was modified cast iron just to avoid that high brittleness of the material. So usually most of these piston rings now are out of ductile for that reason. You know, oftentimes they'll be a little bit mishandled at the assembly. You know, people want to stretch them a little bit more than they have to get them over the piston and back inside. So, but anyways, those are the metals that you'll find in the industry. And other than these cast iron rings, in the sealing industry, metals, that's about it. Now we get into sealing compounds, and the sealing compounds we're going to look. They're all egg-based, right? Egg-based in the sense they're all thermosets. Okay, and we're going to look at some of the things you got to look out for when you're trying to choose a material. Then we're not going to spend hours on each compound to get the pros and the cons and the details. And there's, well, all right, let's move. I don't know if Gordon Ramsay did a lot of pastry, but we're going to talk about that. Baking a cake here. Sealing compounds, there's different families. You know, you go to your local restaurant and you're craving for something sweet, so you know you can get a chocolate cake. But every restaurant is going to have his recipe for a chocolate cake, but restaurant A and restaurant B, maybe the chocolate cake doesn't taste the same. Not because it's called a chocolate cake, but everybody's got his recipe. Oh no, I don't want a chocolate cake. I want what's that red one called now? That's I forget. It's a big. Anyways, you'd rather have an angel food cake. Well, you know, then again, that's another recipe. Or you want a Linzer tort if you come from Austria or from Switzerland. Oh well, that's another recipe. But it's like a compound. We're mixing stuff together until we get a recipe that we like. But you go to your in-laws for the weekend and they ask you to bring a chocolate cake, but you're going to make one too, and then you're going to have a little contest who makes the best. Well, nobody makes the best. They're all different because everybody's got his own recipe. Sealing compounds are the same. So we'll look at the big families, what you should be looking out for when customer calls and saying, what should I use or what should I be looking for? You know, we could talk hours about this, but I'll just give you some of the main guidelines. All right, we're gonna go back to our rubber compounds, our thermosets, and we'll use our kitchen vocabulary to discuss what you look out for. Okay, so your rubber compound is made of a base elastomer. So if you say my rubber is a nitrile rubber, well, you're going to have a bit of nitrile, like you'll have cocoa powder in your chocolate cake. But base elastomers is usually 20, 30, 40% of the whole entity. And the fillers is what you put in that's cheaper than your base elastomer. That's going to give us better mechanical properties. And usually most fillers, we use carbon black. Carbon black, that's why most of your rubbers that you'll find in the industry are black. Though you find colored rubber, we'll get into that. No, why don't we get into that right now? Okay, you can take out the carbon black and put clear fillers like silica. And what that does, it allows you to pigment the silica after. You know, you'll find that some of your fluorocarbons are brown, some of your neoprenes are red, some of your EPDMs are purple, and that's the way you do it. So kind of like adding food coloring to your angel food cake or whatever. Anyways, so you get the fillers. The plasticizers is what gives good modulus, good flexibility, good resilience is the plasticizer. Good low temperature resistance is modified by your plasticizers. The curing agent is your baking powder. Is basically when you cure your rubber, when you're vulcanizing it, it's the agent that gets in a cake, it would be what gives it to rise and give it its if you don't put any baking powder, it's going to come out flat and it's going to be hard. Well, your curing agent will help you keep that flexibility it'll enhance the whole vulcanizing process as it's put in either the aging oven or whatever other vulcanizing process you use. And special additives could be color, could be low temperature resistance, could be additives that are required to make it sanitary acceptable. It could be a variety of things, kind of like your cake. You could add extra flavoring or you could add whatever. So that's what you have to make a rubber compound. So you call it nitrile, but it's not, or you call it EPDM. It's not 100% EPDM. It's the base material and the rest you fill it. Why am I holding this? There you go. That's what you make. And then we're going to take a look at, you know, what makes a chocolate cake, what makes a vanilla cake, what makes I'm still forgetting. Oh, red velvet, that was the one I was looking for. Okay, they each have their recipes. So we look at a nitrile rubber. Oftentimes, we'll use this one. The other ones will be different materials, but repeats of the kind of same characteristic stuff you got to look at. So you put its generic name and the abbreviation of the material. up to industrial standards. They're not always the same, as usually you have ASTM standards, which is what is it? American Standards for Testing and Materials. ASTM use lettering, usually, and then you have the ISO DIN, which is the European version of their standards. Usually the letters are the same, but sometimes they might have a one-letter difference, as we'll see as we go along. So nitrile, that's what you'll find it listed under often. Temperature range. Temperature range, you have to be careful, because these are average temperature ranges. We have nitriles that will go higher than that. We'll have nitriles that will go lower than that. But if you buy a standard off-the-shelf nitrile without asking for anything special, this is roughly what you're going to get. You know, and the big thing about nitrile, it's general purpose. So it'll handle petroleum oils, you know, ethylene glycol fluid, sort of what you've got in your car radiator, the antifreeze, etc. Cold water, silicone greases, does, you know, pretty good. It's not really recommended for air exposure. What do we mean by air exposure? It doesn't age well when you leave it outside. Your garages might have told you once, and as we're filming this, it's here in Quebec, it's starting to be the craze for winter tires, and oftentimes they'll take last year's winter tires in their garages. So he's trying to make an extra buck. So he said, "Oh, look at your last year's tires. You didn't warehouse them very well. Look, they're full of cracks, but I'll sell you 4 new tires at a really good price." Salesman. But it's because that affects car tires. But air exposure, usually nitrile is not the best. Ketones is all your polar solvents. Example, your nail polish remover, which is acetone based. If you're running paint lines, methyl ethyl ketones, those things. We're not going to waste our time on halogenated hydrocarbons, because I haven't, in 40 years, I don't think I've ever run into any. So call me in 40 more years and we'll see. But this one's important. Automobile, aircraft brake fluids, what you've got in your car master cylinder, okay? No, you can't use nitrile, okay? And strong acids. So that's kind of what you got to look for, you know. Once you see general purpose, that's why you buy a cheap O-ring kit from whoever, and it's got like 320 sizes in a box. General purpose, throw it in the back of the pickup truck and you can fix most of the stuff. And of course it'll have its limits, but again, these not recommended in here. Very rarely that on a repair job you'll run into those, more on very specific applications. You know, mechanical properties, good permeation. That means if you have a bit of a vacuum application or pressurized gas, it doesn't go through the material. Good wear resistance, you know, wear abrasion, and it's got good, not great, but good compression set and short-term resilience. Remember what compression set is. The compression set is the value that decides how much memory the material has once it's been compressed. So a good compression set means that you compress a material and after a while you release it, it hasn't lost a whole lot of its original size. The more original size it loses, the worse it's going to be as a seal, because all of a sudden your O-ring's not going to, or your rubber piece isn't going to be able to touch either surface, so it's going to create a leak path. So anyways, so that's what you're going to look for, and I think we got 5 or 6 slides, and we'll just try to give you why the next one's going to be different than this one, but we don't want to spend hours on that. Not that I don't like you, but time is of essence here. Time is money, right? Okay, highly saturated nitrile, okay, modification of the nitrile recipe to enhance the high temperature in. And that's what that's why I say sometimes between the ISO DIN and the ASTM, you might have a little bit of difference. HSN for highly saturated nitrile, or HNBR for, again, a highly saturated NBR nitrile. Okay, we didn't do much for low temperature, but we did a lot for high temperature. Recommended for, you know, we didn't have that on the other one. R134A, yeah, whoopee, what's that? That's your standard refrigerants, like it's a Freon that you'll find in most AC systems, especially in cars. And your water glycol steam, it's much better. Petroleum oil is the same, a little bit better in air, good silicone greases, but we haven't solved the polar solvents, which was your acetone, you know, your nail polish remover, your acids, your chlorinated hydrocarbons, which I haven't seen in 40 years. Fuels, it depends what kind of fuels, and this one is a little bit of a misnomer because I think it applies more to aircraft fuels, but what you get also now is you're getting a lot of the E85s, these ethanol-based ones. You have to be a little bit careful. And again, auto and aircraft brake fluids doesn't change. Same mechanical properties. So really, what you're getting mostly out of highly saturated nitrile, really for not too much more money, you're getting a lot of better high temperature resistance without getting into the more expensive elastomers like the fluorocarbons, etc. Okay, and you're getting a little bit better steam resistance, refrigerant resistance. So you're gonna, again, you look at your spec sheets, you know, you look at what it's called, what the temperature range is, and most handbooks that you could get from any manufacturer will kind of give you this, you know, maybe present it in a different fashion, but you know, you really need to look what's recommended. And remember again that infamous second slide that I always refer to about the last things you got to check when we talk about media compatibility. Got to make sure not only your fluid, but all your lubricants, your contaminants. You know, if you're in a place that uses a lot of polar solvents and you're in a dirty work environment where you can get polar solvents that are left behind on a workbench that hasn't been cleaned up, you got to just be careful what you're using so you don't just drop your O-ring in a puddle of something and all of a sudden it's 3 times the size when you pick it up again. Just be careful. Fluorocarbon, A-type because it's the most popular. Okay, FKM is what we use in North America. That's the ASTM designation. FPM is the ISO DIN. Basically kind of same stuff. Temperature range, notice it's good at high temperature, but not very good at low temp. So you got to keep that. Remember, it's always a question of compromise. You're going to use this one because, ooh, it's great. It goes high temperature, but you know, for you who live in cold weather, winters, especially when it gets like -20, -30, -40, and more, unfortunately, not a good material. Okay, and why this is an average, we have available low temperature fluorocarbons. They cost a fortune, but it exists. You can modify your cake recipe to get a A-type fluorocarbon that's good for low temperatures. Actually, might not be called fluorocarbon A, might be fluorocarbon GLT or things like that. But again, you look good for petroleum, good for the lubricants, silicone, those infamous halogenated hydrocarbons, which nobody ever sees, but it's good for that if ever you do see it. Acids. Black is a better material in acids. It doesn't mean that your colored ones are not going to work. It's just if you have high temperature acids, the carbon black doesn't react as much as the silicone ones. But all has to be taken, you know, with a little bit of judgment here. If you wanted the best of the best, I would say always keep your fluorocarbons to the black. Not only does the black give you a little bit better resistance in high oxidizing environment like hot acids, it also gives you better abrasion resistance because carbon black is better as a filler than the silica fillers. Not recommended. Again, your Nail polish remover, fluorocarbon, even though it's sold like 3, 4, 5, 6, 7 times the price, still doesn't handle ketones, still doesn't handle auto and aircraft brake fluids. So, little lesson here, it's not because everybody tells you it's a great material or it's gotta work because it's really expensive, and it's not necessarily true. Those are the proof. Ammonia and hot water and steam, especially. A lot of people that you're using autoclaves or that are steam cleaning parts because you really got to get the crud out. You have to be careful if you're using fluorocarbons. Fluorocarbon has a tendency to hydrolyze fairly quickly in hot water and steam. What does it mean? The material gets brittle, it gets cracked, and to the extreme it breaks down like cracker crumbs. So just be careful. Good wear, but not as good. We'll see pretty soon on the last slide. Excellent compression set. Fluorocarbon, one its great advantage, you compress it, comes back to its shape for a long, long time, and has very, very good compression set values. Okay, and you know, I don't know why I say moderate short-term resilience, but I would say good. So those things we've got to look at. Again, EPDM, which is ethylene propylene. Everybody in the whole wide world uses EPDM. Okay, temperature range, really good in the cold, huh? Okay, and you look at it, it's good for a lot of stuff. You know, whether you leave it outside, it's going to last forever outside. Brake fluids, great. Remember, none of the others do well in brake fluids. None of the other ones really do all that well in steam and water, even though HNBR is a little bit better. Acids and bases, as long as they're dilute, not bad. Ketones and alcohols, it's all great. So it looks on the onset like a better material because it handles cold and it does all this. And then we cross over to the not recommended for, and then we just burst your balloon on this one. Can't use it in petroleum oils. So if you work in the hydraulics industry where you're using petroleum-based fluids all over the place, can't use this one. But if you're running a system that's running a hot water and steam as your fluid media, it's great. So you've got to be careful. But again, if you have a system that runs on hot water and steam and you use that, but the person who assembles the cylinder isn't careful and he uses a petroleum-based grease to grease up his seals before he puts them in, guess what? Surprise, can't use those. So again, good wear resistant, good. So really, it's good for everything except probably what 90% of you listeners are going to be looking at, petroleum-based oils. Now we look at silicone, and everybody has silicone somewhere in their house, whether it's doors, windows, pressure cookers, computer chips. Silicone as a rubber that we'll find in the industry. It's great for its temperature range, and of course that SI is universal. Look at this. And apologize, I just noticed those are all F ratings because a lot of our North American manufacturers for rubber still listed in Fahrenheit. The nice thing, you all own cell phones, and probably on your cell phone you can either use Mr. Google or anything else, and it'll give you the conversion into Celsius, the Celsius scale. But still, really wide temperature range, which is good. The rest you have to be careful on silicone. Okay, so it's good for dry heat. Some petroleum oils, then that's when you have to get picky, and whoever your vendor is for the silicone, ask your questions depending on who your source of supply is. This is my product that I'm using, and then will silicone hold up? Your vendor should be able to help you out on that. Maybe your vendor is Mr. Google. Mr. Google can also help you. Mr. Google does lots of stuff, you know, even how to bake a turkey or something, whatever. Low temperature, it's great for low temperature. And you'll find a lot of silicone that are used outside applications where it's not in contact with ketones, acids. silicone, and auto and aircraft brake fluids. And some petroleum oils, again, and I can't give you the listing, we'd be here all day. But things you gotta look out for, but the most important thing that you gotta look out for is silicone, which people don't think of. Mechanical properties, extremely poor wear resistance. Silicone does not wear well, so if you're using on any dynamic application, you cannot use, never say cannot, you should never use a silicone in a dynamic application because it's going to wear just like a rubber eraser. That's its mechanical properties are not good. It has poor permeation resistance, so if you're pressurizing air or if it's used in a vacuum application, it's going to get pushed or sucked right through the the core of the material. But it has excellent compression set. So what we've just found is that every elastomer has its strengths and it has its weaknesses, and the important thing is, and that's why we left those slides as simple can be, just so that you have an idea of what to look out for. And it's not a complete list, but it's a good indicator. Okay, and usually most of the handbooks that will be published by rubber manufacturers, whether it's rubber, whether it's O-ring manufacturers, whether it's hydraulic seal manufacturers, they'll usually have these types of charts. I was going to say somewhere's in the book, except I'm the one talking to you about the books, but I know this generation here, no, they didn't go in books anymore, you just go online. So, always kind of look out for that. We've got, I do believe, one more, polyurethanes. We use polyurethanes extensively in hydraulic applications because this here, excellent wear resistance. Polyurethanes' biggest claim to fame is it does not wear out, okay? High abrasion resistance. That's why a lot of your seals in a hydraulic cylinder, where there's a lot of dynamic movement, you use polyurethane because it's the best wearing material you got. So excellent wear resistance, poor compression set. It's all based on the compounding. Right now you get polyurethanes a much better compression set in the past few years than you had for the last 10 or 20 years. It's improving, but it's not typically not as good as a nitrile or a fluorocarbon. Good short-term resilience. Petroleum oils good. Hydrocarbon fluids good in ozone. Again, and like the other ones, not good in acids, not good in ketones, not good in that, and not good for brake fluids. And if you look at the temperature range, this is very, very average. So if you know what your temperature is going to be, and it doesn't fall within the parameters listed on this slide, call your vendor, because there's so many compounds available now. We're going back to a chocolate cake. There's so many iterations of the chocolate cake that I know there's some polyurethanes that will take it to 275, 300 degrees F. Minus 65 it varies. Minus 65 means the material is still good, but on a really cold day in the winter time, it might be a little stiff. Other thing we'll talk about, I started from the bottom and working my way back up to the top, just to be a little different. Okay, your code names in the industry, AU is the standard. When the polyol, which is one of the two parts to make polyurethane, you need a polyol, you need a diisocyanate. Sorry for the chemical terms. Most of what you get in the industry is a polyester, but some manufacturers prefer polyether. We'll have a quick look in the probably next slide or close to it. And then if you see EU, it's because it's a polyether base, and the AU is a polyester base. So here's the difference. Polyesters typically have superior chemical and high temperature resistance. So high temperature hydraulic oil and the inherent heat frictional heat that's developed. And I say typically because like in anything else in life, exceptions exist, but polyesters will handle that better. Polyethers, on the other hand, have an advantage over polyesters at low temperature and in high water-based fluids. So depending on what you're using, and again, it's not this and nothing else but, you know, I'm sure there's some polyethers that have good chemical and high temperature. There's some polyesters that might be able to work pretty well in high water, but generally that's the difference between the two. Other designations for polyurethane, a lot of people call it PU for guess what? Yeah. What was his name? Pepe Le Pew, for those who are Bugs Bunny fans. Okay, PU, thermoset, polyurethane. So set, okay? And if you see TPU, well, TPU is not a great material if you're going to use it in hydraulics because it's a thermoplastic. So it's starting to get really hard, and it has those characteristics where, you know, there's no cross-linking. So it's great hard material. Well, you can use in backup rings and stuff like that, but just to be careful. But again, not everybody, some people call it AU, some people call it EU, some people call it PU, some people call it TPU. You know, everybody's got their own vocabulary. And we got one more slide just to make your life even more miserable. Other descriptions to define diisocyanate. Remember we talked about the polyol part, which is either, sorry, either the polyesters or the polyethers. That's the polyol section. The diisocyanate, you have MDIs, TODIs, PPDIs. You know, each manufacturer uses kind of. The PPDI is the latest version, and I'm just going to throw you a name, but don't quote me on that as being exclusive. We're just using it because those are the things that are sold often. PPDI, Parker has a big line of their PPDI products. The TODI has been Freudenberg sealing technology. That's been their hobby horse for the last 50, 60 years. And it's another great material. And the standard material for most people is MDI, but that you'd need to do a little bit more studying in, you know, in your chemical backbones and structures and all that. But just in case you see those, you know, you don't have to remember. Just say, yeah, I saw it somewhere. Somebody talked about it in this lousy video that's on somebody's server here. So you'll know that you might be able to see that and give you an idea. At least you won't be strangers. This one is important. This one is to give you a quick guide to what works and what doesn't. Okay? Wear resistance. So we've separated that. Well, no, maybe that's not the right place for the camera. Sorry about that. Okay, we've put a wear resistance over the different families of material. And of course, we didn't talk much about carboxylated nitrile or polymite, which is an elastoplastic, but those of you people who have used Parker products before might recognize. But it's just important if you go from worst to best. Okay, wear resistance, fluorocarbon. Well, we say it's great in max temperature. Okay, but you take it in water and you lose, and you take it in wear and you lose. So you want the best wearing material, wearing, the one that wears the best. Okay, and you'll look at 10. Remember we said polyurethanes have great wear resistance in dynamic application, but they're also the worst in water. And now you see a whole lot more water-based fluids in hydraulic systems, so you have to be careful. Oh, we use polyurethane because it's great. It's #1 in for wear resistance. Yeah, but you're using it in hot water and it's not going to resist as well. But again, here's the exception to the rule. Now there's a lot of polyurethane recipes on the not standard, not necessarily on the shelf, that do better in water. Okay. and the max temperature. So you got to look at these two. You know, max temperature, we've already had it on the slide before, but your wear resistance and your max temperature in water, you've got to look at those two, especially the wear resistance. People think, oh, fluorocarbon, yeah, that's the one, you call it Viton, right? Oh, yeah, yeah, and it's 5 times the price, so it's going to be good in wear resistance. No, it's the worst. So they're just things to look at. They're general guidelines, and don't take that all the way to the bank. Use a little bit of discernment, or call your vendor, or call your technical director, or call your engineer, or call 911. But it's just to give you an idea of some of the things you need to look out for when you select an elastomer. Things to watch out for, and we'll finish with this. The guy's a pain in the neck, right? Always keep in mind the selection criteria is listed on page 2. So every time we start with this, we finish with that. In the middle of the presentation, we go back to that. You're going to say, do you have anything else new to talk about? No, but you should always keep in mind the selection, and it's important. You know, temperature, pressure, fluid, application, expectation, keep in mind. Validate your material selection according to the resistant to, again, I go back because oftentimes you know what goes in a cylinder, but you don't know what goes before everything gets installed. So to all fluids, media that can come into contact with your chosen material. So on somebody's workbench, or on somebody greasing up a seal, or whatever, make sure that all along the rebuilding exercise or the installation exercise, there's nothing funky that gets into the mix that could affect your seal. Material hardness must take into consideration the sealing requirements. Okay? Material conformity. Remember we said conformity is the softness. Okay? So this is where, again, compromise is a big thing. Okay? If your material conforms to the surface finish, to the peaks and valleys of your surface finish, if it conforms, it's going to seal well. Okay? So I would say get the softest material you can get, because it's really going to conform. You know, it's easier, like soft putty. Problem is, when you get higher pressure, you don't want it blown out of the groove. You don't want to get extrusion. So you have to have enough conformity to seal and enough extrusion resistance to not get blown out. Okay? Or if you're using it as guiding requirements, but mostly in the extrusion. So that's when you have to look at your pressure charts, and that's when you ask questions and check your material, what each material can handle pressure-wise. We had that graph at the beginning. We were showing you from 70 Shore-A nitriles all the way to nylons and PTFEs. Got to check that. And the other thing that we often forget is you can get, oh, well, I got really high pressure, so you get some nice hard material, except your mechanic, no way to install it. It's way too hard. So you've got to figure that into the equation. You know, can you install a hard seal? And that's why some of the seals, dynamic seals, out of thermoplastics, well, they're split. They're split because if they're a solid ring, you'll never get them on. Okay? And this one, that's my hobby horse. This is my fixation on data that I think is important, that nobody else talks about, so whatever. Compression set values will be your ultimate guide of sealing performance and long service life. That means you can buy your seals. If you look in a book, every manufacturer should or does publish the compression set values. What's a compression set? If you compress your material and you leave it compressed for a while, then you remove the compression and you see to what dimension the seal returns back to its original shape, and whatever it's lost, what it's lost is your compression set. It has been set. Okay? So as your number gets higher in the compression set values, it's a worse material. So if you have a 10% compression set, that means it only lost 10% of its original compression. If it's a 60%, then it's not a very good material. So a good material, good compression set, and it's available for everybody, whether it's your vendor, whether it's on the web, or whether it's in catalogs. Those things are published, but you kind of have to look for them, okay? And it's not based nitrile is good. Some nitriles have, on the same test, will have a 25% compression set, and some will have a 60% compression set. Because what? It's recipe based. You can modify your recipe. So compression set, it's available. It's kind of the forgotten son. Nobody really consults compression set values. I say a good compression set, guarantee a long service life. So that's it. And that's it. Thank you. So have a nice day, and thanks for listening.